Hello everyone, welcome to the channel TOC. In this video, we'll see the grammar to language conversion. So in the previous lecture, we have already seen how to convert a language into an equivalent grammar. In this one, we'll see how to convert this grammar into the language. So in this video, I'll discuss three examples. I have three grammars here, G1, G2 and G3. So one by one, I'll tell you how to convert these grammars into equivalent languages. So if I talk about the grammar, we know that grammar has four tuples, namely Vn, sigma, p, s, where Vn is a variable, sigma is an input terminal, p is the production rule, and s is the start symbol. So out of those four tuples, p is the most important one. So here I am only mentioning the p, that is the production rules of every grammar. Okay. So from the production rules only, you can find out how many variables are there. You can find out how many terminals are there. You can find out which is a start symbol and so on. So only thing I have given here is the production rules. So in the first grammar, you can see that we have two production rules. We have s tends to 0, s1, and we have s tends to null. So what I'll do, I'll try to generate all the possible strings from this grammar, because we know that the language is the collection of all possible strings. Okay. So we'll try to generate all the possible strings from this grammar, and then we'll conclude something, and that will be my grammar. Okay. So let's see in this one. So the first rule that I have is s tends to 0, s1, and then we have s tends to null. Okay. So the first string that you can see in this one that we can generate. So here I'm just writing the strings here. So the first string that you can generate, you can see here we have s tends to null. So null, I've already told you in the previous lecture, this null is a string only. Okay. It's a null string. So the first string that I've got is epsilon. Clear? So first thing I have got. Now second thing, I want to generate some more strings. So what will I do? I'll use this rule. So let's see, s tends to 0, s1 I have, and if I put this null value here, what will I get? I'll get 0, 1. So another string I've got is 0, 1. So first string I've got is null, and the second string I got is 0, 1. That is my shortest possible string with zeros and ones. Clear? Okay. Again, I can use this rule only, that is s tends to 0, s1. Now in place of this s, I can put this rule again. Okay. So let's put this one. So 0. So on this s, I'll put 0, s1. So I'll get 0, s1 followed by 1. Now if I want to terminate this one, that because I know that with s I have to derive any particular string, and this derivation should not contain any variable. So I should get rid of this s variable. So how will I get rid? I'll use this particular rule, that is I'll put null here. So I'll get 0, 0, 1, 1. So next string I've got is 0, 0, 1, 1. So 0, 0, 1, 1. I've got my third string. Now again, let's see what else I can generate. Again, I'll use this rule only, that is s tends to 0, s1. Now on this s, I can put 0, s1 again, 0, then 0, s1, 1. On this s, I again can put 0, s1, that is 0, 0, 0, s1, 1, 1. And then to terminate, I can put null here. That means I'll get 0, 0, 0, 1. Clear? So the next thing I got is 0, 0, 1, 1. Clear? So I can go on and on. So I can generate any number of string in this one with equal number of zeros and equal number of ones. And you can see in this one that the strings are always starting from 0 and the strings are always ending with 1. And the number of zeros is always equal to the number of ones. So the language that I can generate from this one is, what is the language? We have the strings as 0, and this goes to n power. Then we have 1 n power, where the value of n is greater than equal to 0. Now why it is 0? Because the first string that I got is null only. That means if I put the value of n here as 0, 0, then only I can get a null value here. So that's why we have put the value of n as greater than equal to 0. So if the value of n is 1, I'll get 0, 1. If the value of n is 2, I'll get 0, 0, 1, 1. If it is 3, I'll get 0, 0, 0, 1, and so on. So this is the language 0 to the power n, 1 to the power n, where n is greater than equal to 0 for this particular grammar G1. Now let's see the next one. The next grammar that I have is G2. It says in this one we have 1, 2, 3 production rules, and in this one I have two variables S and C. In the previous one we had only a single variable. Here we have two variables S and C, and the terminals, input terminals we have is A and B. In the previous one we had 0 and 1. Clear? So in these three production rules we have S tends to ACA, C tends to ACA, and C tends to B. So let's see how many strings I can generate from this one. So I'll just write the strings here. Okay. Now first rule is S tends to ACA, because any string which has to be derived should be derived from the start symbol only. So I'll use this rule only. So S tends to ACA. So on this C I can put this value. Okay. So what I'll get, S tends to ABA. Now this is my shortest possible string. Okay. So less than this I cannot get any other string. Clear? So I've got one string, that is ABA. Clear? Okay. Again, let's see. We have S tends to ACA, and then on this C I can use this rule also. So what will I get? I'll get S tends to A, then I'll get ACA followed by A. Okay. Now to get rid of this C, what I'll do, I'll just simply put this value here. So what will I get? I'll get S tends to AA, B, A. Clear? So the next thing I got is double A, B, double A. That is double A, B, double A. Clear? Again, S tends to A, C, A. Clear? Now on this C, I can put this value. So I'll get A, then ACA followed by A. Again, on this C, I can use this value again. I can use n number of times, no problem. Clear? So I'll get triple A, C, triple A. Now to get rid of this capital C, I will use this particular rule. That means I will get triple A, B, triple A. So another string I got is triple A, B, triple A. So I can go on and on and on and on, and I can generate any number of strings, and in every string I can see that the string will always start from A, it will always end at A, and the A's are basically being divided with B in between. So B is actually acting as a divider. Okay. So first part of the string contains A's, second part of the string contains as many A's as were there in the first part of the string, and there is only one B in every string. So the language that I can generate from this one will be, it will be A to the power n. Okay. Then we have B, then we have again same number of A's, that means A to the power n, where n is greater than equal to, not 0. Why? Because we are not generating any null here. Okay. So that's why we'll put 1 here. So A to the power n, A to the power n, where n is greater than equal to 1. So this is my language for this particular grammar. Now third one, the third grammar that I have is G3, and in this one I have 1, 2, 3, 4 production rules, and let's see how many strings I can generate from this one. So I'll just write the strings here. Okay. So the first rule, I can use any rule. Okay. So what is the shortest possible string I can generate? So I can see here only that I'm generating a single digit string. So the shortest possible string will be A, or it will be B also. Clear? Now let's use this rule. So S tends to AS. Clear? Now to get rid of this S, I can put either this value or I can put either this value. So what will I get? I will get A if I put this value, or I'll get AB if I put this value. So I've got again two more strings, that is AA and AB. Correct? Now again, let's see. S tends to BS, I'm using this time. BS. So what will I do? To get rid of this S, what will I do? I'll put either this value or this value. So I'll get BA or BB. BA if I put this value, BB if I put this value. So again, I've got two more strings, that is BA, BB. Okay. Now let's see any other thing I can generate from this one. So again, say I'll use S tends to AS. Clear? S tends to AS. Now in this one, I again can put AS only. I again can put BS only. So let's put AS again. So A, again on this S I'll get AS. Clear? Now in this S I can put again BS also. So AA BS. Okay. Now on this S I can either put A, I can either put B also. So if I put A, I will get AA BA. If I put or if I put B, I'll get AAB BB. Okay. Or I can get any other value also, like if suppose if I want ABA also, so I can get ABA also. How will I get? I'll use this rule, then I'll put this value, then I'll put this value. So you can say this grammar generates all the possible combinations of A and B, okay, but excluding null. There is no null in this one. Okay. So what I can have, the language for this one will be, it is all the possible combinations of A and B. Any combination you name it, it will be generated from this particular grammar. So for the language, what I can have, it will be A comma B star. Now what is this star? This A comma B star is called as the clean closure. Okay, this means all the possible combinations of A and B including null, but we are not getting null here. So what will I do? I'll just do minus epsilon here. Okay, now this is equivalent to A comma B plus. Now this A comma B plus is called as the positive closure. This A comma B star is called as the clean closure. This is called as the positive closure. So I'll just write it here. This is called as the clean closure, and this one is called as the positive closure. Okay, so the language generated for this particular grammar is A comma B plus or the positive closure of A and B. So this is the way how we convert a grammar into an equivalent language. Thank you so much.